Hello and welcome to the Texas Instruments Student Revision Tutorials series, Unit 3, Specialist Maths with it, TI-Nspire, and this is Part 2, Vectors. Hi, my name is Peter Flynn, and what we're doing in today's webinar is we'll look at position vectors as functions of time. We will look at parametric and Cartesian equations. We'll look at the motion of two particles and whether in fact they collide or not. And we'll also offer a brief introduction to vector calculus and applications to curvilinear motion. Curvilinear is a fancy term, means motion not in a straight line, so for example projectile motion or circular motion. So I'll just move now to my TI-Nspire file. I've used Cambridge Specialist Maths Unit 3 and 4 as an occasional reference in this session. Okay. First thing we want to look at is we want to look at the way in which we describe curves in the plane using vector functions. And so our prompting example is to find a Cartesian equation. Now a Cartesian equation is y in terms of x, and that can be a function or it could also be a relation. For the graph represented by the vector function, r of t is t plus 1 I plus t squared plus 2tj, where t in this instance is a real number. Now, in a by hand environment, what we do is, well, if we go back, first of all, x of t in this instance is given by t plus 1, so x is t plus 1, and y of t is t squared plus 2t. So in other words, y is t squared plus 2t. So we have x in terms of t and y in terms of t. In terms of a parameter, and there are two what are called parametric equations. And what we do is we attempt to eliminate the parameter t to try and form a relationship between y and x. So as we see here in the solution outline, our first parametric equation is x is t plus 1, and our second one is y equals t squared plus 2t. Now in this instance, the best approach would be to express t in terms of x from equation 1 by making a simple rearrangement. So therefore t is equal to x minus 1. And then substitute that into equation 2. And what that does is it removes any reference to t in the second equation. So by making that substitution, you get y equals x minus 1 all squared plus 2 lots of x minus 1. You can take out a common factor there of x minus 1, and you're left with x minus 1 by x minus 1, etc. So you end up with a difference of two squares actually. You end up with a product of x minus 1 and x plus 1, which when you expand you end up with y equals x squared minus 1. Now because t could take any real value, the link between t and x is here, also here. So if t can be any real value, then so can x. So that is our Cartesian equation. So we're expecting to see a parabola. We could graph that parabola using function graphing. We can also graph parametrically, so which will form an important part of this session. So let's show you parametric graphing. So we click on and make the graph screen active. What we do is we press menu, then 3 for graph entry edit, and then number 4 for parametric. And our entry line is different. It's no longer f1 of x equals. It is offering us to put in the parametric equation for x in terms of t and the parametric equation for y in terms of t. So what we'll do is we'll say that x1 of t is t plus 1, and then down arrow, and then y1 of t is t squared plus 2t. Now we want t to be part of the real, so what I'm going to do here is I'm just going to choose quite a reasonably large negative t value, so say negative 100, and then a reasonably large positive t value, say 100, and we're graphing at a t step of 0.13. So that should be all right. What we're expecting to see is we're expecting to see a parabola with equation y equals x squared minus 1. and when we press enter, that's indeed what we see. Okay. So that's a very brief introduction to parametric graphing. We'll come back to that a few times during the next 25 minutes or so. Go to the next page. We now want to look at the motion of particles. So position vectors is a function of time in the plane. So in the plane denotes 2 dimensions. So when a particle moves along a curve in a plane, its position at any time t is specified by a position vector or a vector function in terms of t. R of t is xti plus ytj. So I and j are the unit vectors. Unit vector I in the positive x direction and unit vector j in the positive y direction. And our parametric equations there are x of t and y of t, and that's shown in that diagram there. Here is another example. It's find the Cartesian equation of the path of a particle which moves such that its position vector at any time t is given by r of t is cos squared ti plus sine squared tj, and in this instance t is a real number. Sketch the path of the particle and describe the motion of the body. Okay, so let's have a look at a solution outline, and then let's see how parametric graphing can help us understand the motion. So in this instance, our parametric equations are x is cos squared t and y equals sine squared t. Now, using or exploiting the Pythagorean identity cos squared t plus sine squared t is equal to 1, if we added 1 and 2, what we get on the left-hand side is x plus y, and on the right-hand side, we end up with cos squared t plus sine squared t, and that's always equal to 1. So that's another trick to be able to eliminate the parameter t. So rearranging to make y the subject, we therefore get that y is equal to 1 minus x. So we have a straight line. Where do we get this fact that x lies between 0 and 1? Well, in general, cos t lies between -1 and 1. But cos squared t, when you square it, anything that's negative becomes positive, will lie between 0 and 1. So in other words, that x there, if you replace that with cos squared t because of that link, we're making that link to say that, well, okay, the domain here is going to be between 0 and 1. So to formally describe the path of a particle here, it's a straight line joining 1, 0 and 0, 1. Question is, where does it start? Does it start at 1, 0 or does it start at 0, 1? Well, a graph will help describe the particle's motion. You can also get a sense of where the particle starts from by substituting t equals 0 into your parametric equations. So let's go to our next page. Now I've taken the liberty to already set up the parametric graphing. So x1 of t is cos squared t and y1 of t is sine squared t. Notice that in the Nspire environment, you can't write the square between the s and the opening bracket there. Okay, so that is cos squared t. And what we see is we see a straight line joining 1, 0 to 0, 1. But how does the particle move? Okay, so if we press menu and go to number 5, trace, and number 4, path plot, you will have access to path plot if you have the most up-to-date operating system, 5.1. So make sure you're always on the most updated, most recent operating system. So from path plot, we're going to go to number 4, path setup. Now our graph type, if we go up here, our graph type, we choose parametric. I'm going to put in, now I know that that's already pi on 24, but we're going to put in pi on 24. It's just, that's a path step that I use often, and particularly when the parametric equations are in terms of sine and cos. So that's more a habit. You could also just simply type in here 0.1, and that would be fine. In other words, it will give you a trace every 0.1 seconds. I have checked the box here. I want to see the future path. All right, so you can either click there or click there to show it again. And I also want to show the point coordinates. So I'll press OK. I'm happy with that. And I go to Menu, Trace, Path Plot, and then Parametric. And what happens is I get an animation button appear. It also tells me that this particle starts at 1, 0, because that's where it is when t equals 0. And all I need to do is press play, and it will give us in this instance, a idea of the particle moving every pi on 24 units of time. As I said, I could have set this up to be 0.1. Make more sense to set it up as 0.1, but as I said, that's out of habit. But what you see there nicely is that again at 2 pi, t equals 2 pi, it's back to where it started again. And that makes sense because cos of 0 is cos of 2 pi, which is 1, and sine of 0 is sine of 2 pi, which is 0. So it gives you a good idea of how the particle moves. And there are some exam questions that are floating around that ask you to describe the motion of the body. And we move on to the next situation. This is a more generalized situation where we've got position vectors as a function of time in 3 dimensions. So when a particle moves along a curve in 3 dimensions, its position is specified by a vector function of that form, where we introduce a z of t, the third parametric equation, and it's in the direction of unit vector k. A popular example of this is a particle that moves in a helical path, or in the form of a helix, where it spirals up. So it's circling, but also travelling upwards in the z direction. We go to the next page. And here is another example in 2 dimensions, or in the plane. We want to find the Cartesian equation of the path of a particle which moves such that its position vector at time t is given by that position vector. Sketch the path of the particle and describe the motion of the body. Now, in our previous example, when we had x of t as cos squared t and y of t as sine squared t, you might have thought that you would get some sort of curvilinear motion. So that might have been a surprise to you that you got straight line motion. In these situations, you have it's a very strong possibility that the particle will be moving either in a circle or in an ellipse. If you've got your parametric equations in terms of tan and sec, there's a very strong chance that the particle will move in the form of a hyperbola. So what we want to do is we want to sketch the path of the particle and again describe the motion of the body. So please understand that these questions you would be doing some by hand mathematics, and also potentially performing some parametric graphing if you want to visualize the path of the particle and also how the body is moving. Okay, so, and I've deliberately left out what T stands for there. So we'll have a look at, go to the next page, and our solution outline. So our parametric equation, so x of t, or x is 1 minus cos 2t, we'll call that equation 1. It's always important to number your equations. And the second parametric equation, y equals 3 sine t, so that's equation 2. Now, this is a circumstance where we need to rearrange equation 1. It's like a combination of the first 2 methods, really. To rearrange equation 1 to get cos t in terms of x. So we've done that, and so cos t is given by x minus 1 over negative 2. And from equation 2, you can simply see that y on 3 is equal to sine t. And we're going to square both these and then add them together. So the squaring and adding exploits the Pythagorean identity cos squared t plus sine squared t is equal to 1. So when we square this one, we get x minus 1 all squared on 4. That's the left-hand side. And we square the left-hand side of this one, we end up with y squared on 9. Then when we add them together, That's our left-hand side. And our right-hand side is cos squared t plus sine squared t, and that's equal to 1. And what we have here is the Cartesian equation for an ellipse. The ellipse has a centre 1, 0. Now the domain, you can tell that the domain or the allowed values for x are from -1 to 3. Now one way of determining that is to look at this first parametric equation, and cos t lies between -1 and 1, so its minimum is -1 and its maximum is 1. So when cos t is -1, x is equal to 1 minus 2 by -1, so that's 1 plus 2, which is 3. And then when cos t takes its maximum value of 1, 1 minus 2 is -1. So that is probably my preferred mode of determining a domain, is from the parametric equation and the rearranged parametric equation. So it's good to have an understanding of the knowledge of the graphs of cos t and sine t as well. Just check to see if there's anything more here. Okay, so a graph will help describe the particle's motion. And what I've taken the liberty to do again is to already graph the Cartesian equation. So you can see it's an ellipse. You can see that its centre is at 1, 0. You can see that the allowed x values are from -1 to 3. But we can also now interrogate the graph to try and work out, well, where does the particle start? What's the period of motion? And what direction does the particle travel in? Does it travel clockwise or does it travel anti-clockwise? So if we press menu, 5 for trace and then 4 for path plot, and then let's have a look at our path setup. So again, I want parametric. Again, I'm going to, by habit, choose pi on 24, and I want those two features checked. So I press OK, and then menu, 5 for trace, 4 for path plot, 2 for parametric. So you see the future path. It's indicating that the initial point for the particle, it starts at -1, 0. You can see by these trig functions that you get a sense of what the period might be. So let's press play and see what happens. Okay, so we're going in increments of pi on 24. Some special points appear along the way for special values, like for example, you know, t of pi, t of 3 pi on 2, etc., etc. So the particle is moving clockwise, and it took 2 pi seconds to complete a lap. So you can see there the period 2 pi on n is 1, so the period's 2 pi. The particle starts at -1, 0, and it moves in a clockwise direction. Now, you can get that by interrogating or studying the parametric equations, but it is very nice to see it visually, particularly if you're a visual learner. Okay, moving right along. Let's look at whether particles actually collide or not. So when a particle collides, when two particles collide, the idea is that they share the same position at the same time. So we've got the motion of two particles. They're described by those position vectors there. And so do the two particles collide? If they do, determine the coordinates of the point of collision and the time of collision. Now, I'm not going to do this example formally. I'm going to show you the graphical representation of it. So we go to the next page, and we've got our two parametric sets of parametric equations graphed. So basically here we've got that's the equation of a circle. So we've got circular motion there, and then we've got motion in a straight line in red. So you can see that the particles designated by position vectors R1 of t and R2 of t, they do at some time share the point, well, they cross the point 1, 2, right? So we know that the two paths, they both end up at 1, 2, but the question is, are they there at the same time, or are they there at different times? If they're at 1, 2 at different times, then the particles don't collide. So let's see what happens here. We press, this is familiar now, menu 5 for trace, 4 for path plot, and we're just going to set it up again, parametric, and again out of habit, pi on 24, and those two boxes checked, and then we press menu, trace, and then path plot, and then parametric. Right, so here are our starting points. So the particle that's moving in circular motion starts at 3, 0, and the particle that's moving in a straight line starts at 1, 2. So the question is, are they at 1, 2 at the same time or not? So we can set them in motion and we can see what happens. We can see from the circular motion graph there, we've got cos of pi t and sine pi t, so 2 pi on n, 2 pi on pi is 2. So the period for circular motion there is 2. But what you'll also have noticed is that the particles never collided. They were at 1, 2, they were at this point, but they were there at different times. And so we have visually verified that the particles do not collide. You would have to undertake some by hand mathematics to algebraically show that. Let's look at another example. You can probably predict in the mind of the teacher here that if the first example the particles don't collide, then the second example they do collide. Be that as it may, the motion of two particles are described by these two position vectors. So do these two particles collide? And if they collide, determine the coordinates of the point of collision and the time of collision. So algebraically, what you could do here is you could equate the I components and solve for t, and you could equate the j components and solve for t. Now, when you do that for the I components, you'll get one solution because you're solving a linear equation. Here you have a quadratic and a linear. So for the j components, you would end up with a quadratic with two solutions. Now, if the solution here, let's say it was t equals 3 for the sake of it, and this one for the sake of it, now that's not correct by the way, I'm saying for the sake of it, and if this was say t equals 3 and t equals 5, then that algebraically verifies that t equals 3 is the time of collision, and you could therefore work out the point of collision. So I've offered the solution outline, but let's have a look at it visually. So again, I've got the Cartesian equation, or the path of the two particles. One moves in a straight line, the other's moving in a curve. So again, menu, trace, path plot, and then path setup, and we're going to choose parametric. I'm going to go automatic this time. Automatic by default, I think from memory, is 0.1 seconds, and I think that it wouldn't be useful here to have a multiple of pi. Press OK, and then what we need to do is menu, trace, path plot, parametric, and we're ready to go. So we've got one particle starting at -310, another particle starting at 2, 0. You can see from the future paths that there is a point where the paths cross, but do these occur at the same time? So we'll set the particles in motion. Right, so we're going up in increments of 0.1 seconds there, and they're nearing each other. You can also answer questions like what's the, if they don't collide, what's the shortest distance between two? There we go. They just collided at t equals 5. So when you solve 2t minus 3 equals t plus 2, you get t equals 5. When you solve t squared plus 10 equals 7t, you end up with t squared minus 7t plus 10 equals 0. And one of those solutions is t equals 5. So we've just visually verified that the particles do indeed collide at t equals 5. And when t equals 5, making that substitution, the coordinates of where they collide is going to be at 735. That's by substituting in. You could substitute into either. Okay, last couple of minutes, we'll just talk about vector calculus, which hopefully you've done in first term. If you haven't, you'll do it in this term. So velocity, consider a particle moving along a curve in the plane with position vector at time t given by that. What we do is we differentiate x of t and y of t, and if they are differentiable, if they can be differentiated, then we can form another vector. You may notice in your textbook and in exams that could be expressed as r dot of t equals x dot of t plus y dot of t. So x dot of ti plus y dot of tj. So the dot also represents first derivative. I've used the prime there. So that's the velocity vector. It's the rate of change of position vector. And the velocity vector is also very useful. It gives the direction of motion at time t. Okay, so all you need to do to calculate a velocity vector from a position vector is to differentiate x of t with respect to t and y of t with respect to t. That's all you need to do. Now, of course, we've also got corresponding situation with acceleration. So consider a particle moving along a curve in the plane with position vector at time t given by that. If you differentiate once, you get the velocity vector. If you differentiate a second time, you get the acceleration vector. So this is the second derivative of x of t with respect to t, and that's the second derivative of y of t with respect to t. So the acceleration is also the rate of change of velocity vector. So what you can do is you can gain information about a particle moving either in a straight line or in a curve about its velocity at time t and its acceleration at time t, as long as you know the position of the particle at time t. So here's a very simple example. Our position vector, we're going to let r of t be 20 ti plus 15t minus 5t squared j. And what we want to do is we want to find the velocity at t equals 4 and the acceleration at t equals 4. The TI-Nspire allows us to perform numerical differentiation. And these questions are done very simply by hand as well, but let's show you the TI-Nspire approach. If this question contained quite a few parts, I'd be very tempted to assign r of t to be a vector in terms of t. And for the purposes of this webinar, I'll show you how to do that. So here I'm going to say r of t, I'm going to assign that by pressing Control Symbols Template. The assign command is a colon equals. Don't use equals, it won't work. So basically I'm assigning r of t to be a row vector. So it's a square bracket to open up. 20t is our in the I component, so it's 20ti, and then a comma to separate the components. Then the j component is 15t minus 5t squared, and we press enter. And so what we've got there is we've got r of t, our position vector, has been defined. Now what we can do is we can work out r dashed of 4. So it's differentiating r of t and then substituting t equals 4 into it. And that will find us the velocity vector at time t equals 4. A shortcut to get the derivative operation or operator is shift subtraction. Then our independent variable is t. Then in here we're going to put in r of t. Then come outside, and now we want the with or the given key. So control equals, and then go 1 to the left, press enter. So we're saying we want to differentiate this, and then we want to evaluate each component when t equals 4. So we substitute in there t equals 4, press enter, and so our velocity vector at t equals 4 is 20i minus 25j. Similarly, we can work out the acceleration vector at t equals 4. So this time what I'm going to do is I'm going to press the catalog button. I'm going to press number 5 for symbols template, and then I'm going to choose the second derivative template there. So press enter, put a t in there, then in this box I'm going to put in r of t, come outside, and then I'm going to say control equals 1 to the left, choose given or with given, t equals 4, press enter, and the acceleration vector at t equals 4 is no I minus 10j. That's actually the acceleration due to gravity, but using gravity acting downwards as 10 meters per second squared. The other thing that you can do is you can find the speed. Now, to find the speed, that is the magnitude of the velocity vector. And to work out a magnitude of a vector in TI-Nspire, you use what's called the norm command. So if we press menu, 7 for matrix and vector, and then 7 for norms, and 1 for, or enter for norm, what we can do is we can go up and grab either the input or the output, press enter, and enter again, and that's telling us that at t equals 4, the particle is travelling at a speed of 32.0 units per second. It could be meters per second, for example. You won't get an exact answer. You'll get a numerical answer because in this instance, because it's a surd, the magnitude of that vector is the square root of 20 squared plus negative 25 all squared, which is the square root of 1025. And when you press enter, that corresponds there. Okay, so that's a nice way to work out the speed. So the speed is the magnitude of the velocity vector. So velocity has a magnitude and a direction. Speed just has a magnitude. So speed is a scalar. Our final example is projectile motion, and I'll just pick the bones out of this one. The position of a projectile at time t is given by r of t is 20ti plus 98 minus 4.9 t squared j, where t is greater than or equal to 0. We can have units for position in terms of meters, so therefore our units for velocity and speed will be meters per second. I'll insert that for the final file that you receive. So the parts of the question are: find the projectile's initial velocity and speed, find the horizontal distance travelled by the projectile, find the speed of the projectile at the instant it hits the ground, and find a Cartesian equation for the path of the projectile. So what you'll end up becoming quite familiar with is when you're talking about projectile motion in the absence of air resistance, the path of the Cartesian equation, the path of the particle, will be a parabola, an inverted or upside down parabola. So if we go to the next page, actually because of time, what I might do is just go through here to one that I've already done and just talk you through it, and that will finish us off there. So what I've got here is the position vector as a function of time. I've assigned it to be 20 TI. It's nice to have TI mentioned quite a few times, isn't it? Plus 98 minus 4.9 T squared J. And so the initial velocity, what we do is we differentiate and substitute T equals 0 in there, which you can do quite readily by hand, no problem. This output is illustrating that the initial velocity is 20I plus 0J. So the initial velocity is actually horizontal. So there's no vertical component in the initial velocity. And of course, the magnitude of that vector is the speed. And you can see there that the speed is 20, let's call it meters per second. Now, just toggling back. So that's part A. Find the horizontal distance travelled by the projectile. So I've been a bit of a smarty pants here. Basically, what we've got is we've got a particle. If we look at the motion of the particle from parametric graphing, you can see that the particle might be on a cliff, for example, and then it's shot off with an initial horizontal velocity of 20 meters per second, and then it basically, acting under gravity, ends up hitting the ground down here. So it hits the ground when the J component is equal to 0. So what we can do is we can use the polyroots command first of all. So menu, 3 for algebra, and then 3 for polynomial tools, and you would use the real roots of a polynomial, and you would get the roots of that polynomial. It's automatically assumed to be set equal to 0, so it's when the J component is 0, so 98 minus 4.9 T squared. I don't want a negative T value because T is positive. So when T is greater than 0, now what happens is your answer comes out to be, in decimal terms, a 4.47, or when you solve that equation, the exact form for the solution is 2 root 5. So that's the T value. Now, what you want to do is you want to take that T value of 4.47, roughly, and substitute it into 20T, and that's why it's 20 times that value there, and it's telling us therefore that the horizontal distance covered by the particle, correct to 2 decimal places, is 89.44 meters. So here, to clarify that again, there's polyroots. So the time for the particle to hit the ground, it takes 4.47 seconds, or in exact terms, it's 2 root 5. Then what you can do is to find the velocity with which it hits the ground, the velocity vector, and the speed with which it hits the ground. This is our magic value. So we substitute that in, and that's our velocity vector. And then to work out the magnitude of the velocity vector, that gives you the speed. So we can see there that the particle, or the projectile, hits the ground with a speed of 48.2, correct to 1 decimal place, meters per second. You can also use your rules of algebra, x of t being 20t, and y of t being 98 minus 4.9 t squared. You can eliminate t, so t is x on 20, substitute that in, and so you end up with a Cartesian equation of a parabola, y equals 4.9 outside of 20 minus x squared on 400. And that's valid for between 0 and 40 root 5, it actually ends up being, doesn't it? 2 root 5 times 20 is 40 root 5. So let's see, to finish this presentation, let's see how this particle or projectile moves. So trace, path, plot, 4 for path setup. I will go in increments of 0.1 here. which I think that's the automatic setting, but we'll type that in anyway, have those checked, and then menu, trace, path plot, parametric, and start. So there's our particle. It's been shot off with an initial velocity of 20 meters per second. So horizontal is the direction, a speed of 20 meters per second, and now gravity is acting on it. It's coming down to hit the ground at about 4.47 seconds. There we go. And you can see there that the distance, the horizontal distance travelled is about 89.4 meters. Okay, so parametric graphing is extremely useful as a visual tool of understanding how a projectile or how a particle is moving, and it gives you some good insight into the direction of motion, if applicable, a period of motion, where the particle starts, etc., etc. So when you're doing questions with position vectors as functions of time and vector calculus questions, your two friends are algebra, the algebra in dealing with parametric equations, and also parametric graphing. So in summary, that's what we tried to achieve today. Now look, thank you very much for listening to this webinar. We hope you found it very useful. In the next 24 hours or so, look, it's likely to be around 48 hours. What you'll do is you'll receive an email with a link to the presenter files, including a revision worksheet and a link to the recording. So look, it's a difficult time at the moment. Hopefully your year 12 is going well. Sessions like this, I hope you found really useful. Good luck with your studies, and thank you very much. Goodbye.